So I'm very happy to introduce John Solitario from Rockset. He's a senior product manager there. And before joining Rockset, he was at Salesforce. And he's also a Stanford man. So without further ado, I'm going to hand over to John for his talk. All vector search is hybrid search.
Awesome. And thank you for the intro. Hey everyone, I'm John Solitario. I'm a product lead at Rockset. And today we're going to start off with a pretty bold claim. And that claim is that all vector search is actually hybrid search. And I know this is definitely going to invite some controversy. So I'm going to skip right to the end. And by starting and skipping to the end, I need to start with the title. All vector search is hybrid search. What this really means is that all vector search applications are actually hybrid search applications. Now, I don't always mean this quite literally, and this is very strongly worded, as this is a talk at a conference. But the argument that I'm going to lay out is that the majority of product experiences are greatly improved when you start to think about hybridizing your search. When you take that pure vector search, which can mean a lot of things, and then adding or augmenting, creating guardrails around that to really increase relevance and increase the quality of your results. Now, bear with me as we go through this, but let's all in this room, assume that this is the case. And with that, we can actually make some really interesting conclusions. And we can actually expand how we start to think about this problem. And so stemming from the first statement, let's assume that all is true, that's something we believe in, then we can get to our next statement here, that all vector search infrastructure is therefore actually hybrid search infrastructure. So if you agree with the first, this naturally flows into the second. But now here's the interesting thing that really ties these two together, is that hybrid search and hybrid search infrastructure is actually a completely new kind of thing. And it's not completely new because it actually borrows from three distinct and seemingly related fields. We can talk about vector search, we can talk about search, and we can also talk about databases, and all the infrastructure involved in these different paradigms. And I know here today, this is a search conference, this is a search audience, but there's a lot that we can learn from other fields. And we can also, by learning from those fields, looking at those fields, can start to see how they intersect. And as they intersect, we can really learn a lot from lessons that we're actually learned perhaps in a very hard way in some of these other spaces and in some of these other groups. And so with that, let's get into it. So I'm not going to spend too much time on this. I know we have a huge range of experience, backgrounds in the room. Just want to really do a quick walkthrough of vector search to make sure we all understand what this is, what it means, why it's important. I'll then quickly run through what hybrid search means, really creating a definition around that. And then once we're all aligned and on the same page about these terms, we can start to think about how they come together and how vector search becomes hybrid search. So what is vector search? Vector search enables us to take these unstructured problems, unstructured data, unstructured statements, and turn those into something that is more easily quantifiable and more easily measurable. We have some ambiguous questions. Show me things I might like. Show me images of cats. We turn those into embeddings. And then based off those embeddings, we're able to search across any type of store that is storing those embeddings, and we can find ones that are similar. So instead of having this unstructured problem, we go from, give me an embedding, let me find the closest or most similar embeddings. And when we think about how to actually do this and how to structure that search, we can always start with our exact nearest neighbors algorithm. This is brute force. This is, given that embedding, search across all my embeddings and return the ones that are the most similar. This works great when you have smaller data sets, but it very quickly becomes expensive as we expand to larger numbers of embeddings, and also as we increase the size of those embeddings. And so to solve this problem, we then can start talking about our approximate nearest neighbor search. Now, using clever algorithms, clever indexing techniques, we can trade off some of our recall or accuracy of those results with efficiency. And with that efficiency, we're actually able to search across these embeddings much more quickly, and therefore reduce the overhead that is required. Granted, we are perhaps trading off some accuracy and the quality of those results. But the moment we start talking about approximate things, this becomes a new source of pain, right? When we think about the traditional database world, everything's explicit, everything's exact. But in the search world, you all have actually been thinking about this problem for quite a long time. I know many of you in this audience are probably very familiar with something like WAN. That's an approximate algorithm that really benefits us in text search use cases. So that's vector search. I now want to lay out hybrid search. Now, I'll spend a little bit more time on hybrid search because this is a very popular and overloaded term at the moment. And it's become very popular in this world of AI and vector search. But I actually want us to take a much broader definition to what hybrid search is. And as we think about this, we can actually think about just combining two or more indexes and acting those indexes to increase relevance, but also potentially to increase performance and efficiency. But today, we're really restricted, or have been restricted, to talking about hybrid search as vector search plus something else. So this true hybrid search, as we can call it, is more or less usually searching across two different embedding types. We have our dense embedding on one end. That's something that may be generated by an LLM or another embedding model. And then we have our sparse embeddings on the other side. But these sparse embeddings are really just a representation of keyword boosting. We create these embeddings, and we can think about associated algorithms like BM25, TF, IDF. And so now we have two different search paradigms. We have across the sparse embeddings, we have across the dense embedding. And then we need to think about combining those results in some way. Now we can use something like reciprocal rank fusion, or something even more simple, like a weighted average of scores. So this, and to date, has really been the main topic of discussion around hybrid search. Well, what about search with metadata filtering? This is another very popular term in the vector search world, and it's treated as a distinctly separate problem. Here's a quick example. Show me the most relevant documents, but those that have been, let's say, updated or created within the past 30 days. And if this document meets my criteria, I can think about really boosting this score, right? Say plus 1,000 to that similarity or to that relevance. And then if it doesn't match, I can think about greatly weighting that score in a negative way. Minus 1,000, or even some cases, minus infinity, right? This isn't something that we would want to show and display in our results. But at the end of the day, this is still hybrid search, right? We're just taking much more extreme weights to that search paradigm and that search approach, and to ultimately influence the output of our results. Now, what about two-stage retrieval and reranking? This is a completely different problem, right? With this approach, we use, in many cases, a very inexpensive index to find, let's say, our initial list of candidates. In this case, we could say it's 100 candidates. And then we may use a much more expensive index or algorithm or model to then rank those 100 candidates and, let's say, return the top 10. Now, this is uniquely different because in this case, we're actually combining two indexes and using the first to maximize the computational resources of the second. But again, we're back to the situation where we're searching and using multiple paradigms, potentially multiple indexes. And so hybrid search actually means much more than just dense search plus a sparse search. We can think about metadata filtering within the lens of hybrid search. And we can also even think about two-stage retrieval within the lens of hybrid search. And this is by no means an exhaustive list, right? Let's think back to that more broad definition. Whenever we're thinking about leveraging two or more indexes to generate results, we can talk about and think about hybrid search. And then we can also combine and mix and match these different strategies, different algorithms, these different indexes in a variety of ways. And so this is how we're kind of leveling up this conversation around what hybrid search means and what it is and how it's going to impact our applications and ultimately our search experiences. And so now I'm going to get into the exciting part of this talk, where we're going to walk through how vector search becomes hybrid search, or why it becomes, or how it becomes, and what this really means. And so let's first lay out what's the dream of vector search, right? I can take a model, I can embed my query, and after I embed that query into this search space of results, I can then pull the most similar items, documents, whatever that may be. And relying on this power of AI, we can turn our nearest neighbor, or to our nearest neighbor algorithms, to really answer and resolve all of our problems around search, recommendation, and Q&A. Now, the slides, as you can see, probably meant to inspire some doubt. And we have one big problem with this approach, is that arguably these models are insufficiently advanced. Now, one day, perhaps in the near future, perhaps in a much further future, this could change, right? We've seen huge advancements in foundational models over the past couple of years. And with that, this could actually change how we think about the problem. But right now, when we generate these embeddings, we run our vector searches, they're amazing at finding semantic likeness or semantic similarity. But they're terrible at respecting specific guardrails. Now, I'm going to walk through a couple of examples to really highlight the argument I've laid out here and laid out at the beginning of this talk, that any product experience primarily powered by vector search is only going to be made better by adding filtering, rules, and perhaps even other guardrails. And this perspective has really been developed from working with a huge range of customers over the past 2 years. And so I want to walk through some of their examples and how moving from vector search to hybrid search has really increased the quality of their products and the quality of those experiences. And so the first example that I'm going to start with is all around in-app search. And in this situation, we can think about kind of a standard SaaS application. In this case, I may be looking for specific objects, let's say specific accounts. And as I'm prompting from that search, there may be very explicit things that I'm calling out and that I'm directing, right? Perhaps I'm looking for all accounts where some of the employees may have worked for Geico in the past. Perhaps I want to limit my search to a certain geography, right? I want to look for the phrase Virginia in my address. Perhaps I'm actually only interested in specific sectors of the economy or of companies. Let's say I'm actually just looking for companies or accounts related to people selling auto insurance. And also, maybe I want to look at instances where our sales team is actively engaged with the account and with the people associated with the account. In all of these cases, we can really think about how we're augmenting this initial, more fuzzy problem of show me relevant accounts. I really want to augment that with very specific data. In this situation, it's text data. You can think about text matching, fuzzy text matching, and a variety of other strategies. That's in-app search. Now, I'm going to talk about recommendations. And so on the screen, I have a screenshot of this product called Whatnot. Whatnot is a live auction site. They have live streams where people are auctioning off goods. And whenever users enter my application, I want to recommend to them a variety of live streams. Now, these live streams are very ephemeral, right? They may only last on the order of magnitude of minutes. And so perhaps I want to make sure that I'm recommending streams that have recently started. I don't want to show them an auction that's at its end, and perhaps they're not even auctioning off any items or objects at that moment in time. Perhaps I also want to show live streams that have a lot of engagement and they have a lot of people involved in the auction, right? This is a much more exciting atmosphere to join in, as opposed to an auction where you may only have a handful of people. So maybe I want to filter for live streams that have more than a certain number of viewers. Perhaps I'm actively looking for very specific items, things that I want to bid and auction on. In this case, let's say I'm actually only interested in sports memorabilia. I really want to restrict the recommendations to this explicit category. And then perhaps I have other functionality built to my application. Let's say I can follow given sellers on my application or on the app. And with that, I want to recommend these sellers that have live auctions going or live streams going that I've followed in the past. And so these are all examples of how we're thinking about augmenting or restricting those recommendations in a variety of ways. And finally, I want to talk about retrieval augmented generation. RAG. I know there's a lot of talks here that are focused on RAG and RAG frameworks and strategies. But for this, we just want to focus on the example. And so in this situation, I'm a major airline, and I've built an application to help my flight attendants, or perhaps anyone working at the airline. I want to give them access to this huge collection of documents, protocols, procedures that should dictate how people can handle certain situations. In this case, whenever a plane is landing into a specific airport, there's actually very specific procedures involved with that process. So let's say I'm flying from New York to SFO. I have a question about, the initial, let's say, kind of pre-landing procedures. And so I actually want to restrict that to the procedures involved with SFO, or perhaps another airport in the Bay Area. This is directly tied to the phrases that we might want to look for. And as we know, in most enterprises, there's so many different documents that can exist that have been created years ago that may be relevant, may be irrelevant. But I want to make sure that I'm only showing documents that have been updated recently, because those are the ones I can have the most trust in. And then finally, what about permissions, right? We have a very specific person accessing this application. We're thinking about this being built across the entire company. We really need to respect, we need to honor, and we need to follow the permissions that are laid out by that organization. And in this case, I only want to surface documents that are actually meant to access or to have access by this given role. And so with this, I hope you all can start to see this value that we have around adding these guardrails, augmenting the experience to create more relevant results and create a more relevant product. And so as we made this jump, as we got on this journey from vector search to hybrid search, we now have this very interesting new problem. Is that we're not only talking about vector search infrastructure anymore, we're actually talking about hybrid search infrastructure. And this problem kind of really highlights a multiple indexing problem. Instead of one single index, that's very clever, very powerful, we have to think how we're searching across multiple and other indexes. We need to think about the cooperation across these, how we leverage them, how we take advantage of them together. And this is when our vector search infrastructure actually starts to look a lot more like search infrastructure and also database infrastructure as well. And we know that both of these groups of technology have actually been optimizing this problem for quite a long time. When we think about any type of query, it needs to access and hit on multiple indexes. So we can actually start to think about how all the advancements in both of these fields, all the great ideas, actually apply to this new problem of hybrid search. But there's a caveat here. And that caveat is that ANN indexes, our approximate nearest neighbor algorithm indexes, are especially difficult to integrate. And so we're going to walk through why that may be. Now I'm going to start with a motivating example. So we're going to start with recommendations, right? Show me the recommendations, but we want those recommendations to respect or to follow certain guardrails or criteria. Perhaps I'm searching for products within an application, right? I want to respect any filters, any information that the user inputs. Perhaps I'm only looking for white t-shirts or white shoes. And perhaps, I want to stick to a certain budget. We can also think about something like inventory, right? We only want to recommend concerts that have tickets available. Or perhaps even friend recommendations, right? We want to recommend friends that are actively online. When we recommend them, you can then start a conversation. And each of these groups of criteria or groups of problems are actually really well solved by completely separate technologies in some way, completely separate indexes. We have this fuzzy problem of showing me recommendations, which, as we can see, or as we all know, can be greatly resolved and helped by something like our vector index. But then we also have this very explicit criteria, right? That criteria is categorical or it's a range. Looks a lot like a series of predicates. And with that, we know this can be very well solved by a relational index. And so we have two indexes here that we really need to leverage and think about using to ultimately solve our problem. And so this gets to two great and obvious, but not great approaches. And we're going to start with the first one here on the left, which is pre-filtering. With the pre-filtering approach, we're actually going to filter out all our vectors that don't meet our metadata filter, right? So we're only going to pull those that meet our criteria. And then with this new set of results, with this new list of candidates, we're going to exhaustively scan those. We're going to perform our exhaustive KNN search, and we're going to find the results that are the most similar. And so this is our pre-filtering approach. And as you can see, this maps one on the first side to a very kind of simple, straightforward, classic relational database query. And then on the second component here, our KNN search, as we talked about earlier. Now, there's another way to do this, and that's with a post-filtering approach. And this is when we apply the filter after we perform that vector search. And so we have this huge bin collection of documents, and we want to pull out all the similar vectors using that vector index. And then we want to filter out the candidates that don't match our criteria. This looks great until we have a little bit of a problem. Perhaps all the embeddings that I had initially extracted, the ones that are most relevant based off of our embedding space, don't actually meet our filtering criteria. And so with that, I may actually have to go back to step one. I actually may need to return more candidates or search a different part of our embedding space to then ultimately get to step two. And what really matters here is the selectivity of our filters, the selectivity of the things and the candidates that we're ultimately looking for. And so with these two obvious but not creative approaches, we can see that pre-filtering works extremely well when I have very selective filters. When these filters are very selective, I'll only return a very small subset of the documents from my larger collection or set. And then I don't need to worry about that computational overhead of performing my KNN or my exact search. But we can really see how this falls apart if I have very non-selective filters. If my filters are non-selective, I'm then returning perhaps almost all the documents in that collection. And then this exhaustive search becomes extremely expensive and also may become much more slower. So then we have our post-filtering approach, right? This works great when the filters are non-selective. As you can see in the previous example, we never get to that third step. We never have to go back, kind of reconsider and repool all of our candidates. But when filters are really selective, you can see us getting in a loop of having to extract documents, apply the filters. They don't meet these criteria, and then we have to go back to stage one. And that can go on indefinitely. And eventually, in some cases, it actually leads to an entirely exhaustive scan of your collection and of your data set. And so now I'm going to switch to a completely different problem. And with this problem, I want you all to imagine a database. That database has two indexes. We have our row store on one end, just kind of your standard relational index. And then we have an inverted index on the other side. And this inverted index provides us a lookup to that row store or to that relational index. And so in this case, I have a mapping from all documents where the name of the user is John to the documents that meet that criteria. And so you can think about this on kind of a field, categorical, and then also document basis. And this ultimately leads to one of the fundamental ideas around indexes, right? One of the fundamental challenges, but also one of the fundamental advantages, is that as we're accessing and extracting these documents, we can think about accessing that row store, scanning that row store. It's actually much faster on a per row access basis. But when we have something like an inverted index, this enables us to look at a far fewer number of rows. But we can start to see a tipping point here between these two access patterns and between these two indexes. And so to highlight this, I'm going to walk through a quick example. We have two queries that on the surface look really similar. In the first query, we're filtering for users where they may have the name John. And in the second, we're filtering for users where their status is active. And you can think about this also, perhaps the status to be inactive, and perhaps we could use a variety of different names here. And although these queries look very similar, they're actually very different. In the first case, we may only have one user with the name John. Probably not going to be the case, but we can imagine there's probably a smaller subset of users with that name. But then perhaps the status, whether it's active or inactive, may apply to the majority of our users, for the majority of rows in the data set. And this creates a new problem and a new trade-off. This implies a tipping point that we're encountering. And that tipping point is directly tied to the indexes that we want to use or access. In the first case, it's going to be much more efficient, much more performant for me to use my inverted index. I can look up the documents where the name is John, and then automatically extract those documents from my row store, and therefore have to pull and scan a much smaller amount of documents and a much smaller amount of pages. Now, in the second case, where almost all my documents meet this criteria, I don't need my inverted index. This is something that I can really look across my entire data set and extract the majority of these that meet this criteria. And so what does this mean? Problem's starting to look somewhat familiar. It really goes back to the selectivity of these filters. In one case, we have a filter that's extremely selective. And in another case, where the filter is non-selective. And based off of the selectivity, we actually want to adopt different strategies for extracting information and extracting documents. And so, what does this mean in the database world, right? Deep down in our system, we have something called a query optimizer. And that query optimizer has two different ways of doing something, two different ways of executing these queries, two different ways, two different options for really selecting which index to use. And the right way to do this is completely based off of the selectivity of these filters. And again, this is all sounding very familiar for multiple reasons. The first one that I want to highlight here is a fairly famous paper that was published in 1979. This paper is all about access path selection within databases. And it's all about estimating the selectivity of filters, of filtering criteria, predicates, to determine which index to use. And this paper highlights a lot of clever ways, a lot of statistics that we can use on our data to actually determine that most efficient approach and how to weigh the cost of these two different search patterns or search paradigms. And with these selectivity estimates for query optimization, this concept, well written about in 1979, is over 40 years old. Seems like a long time ago. What this means is that we've also made 40 years of progress on how to handle this type of problem, how to measure it, where to apply it, so on and so forth. And a lot of this is extremely relevant to things that we've been talking about for really just within the past 2 years, right? When we first really started pulling apart vector search, we started talking about metadata filtering. So it was really back in 1979. And so I want to have a call to action here to everyone in the audience that we should actually really go back and reread and revisit all of the advances and all of the research in both the database and search spaces and think about how we're actually applying that to this new breed, the new realm of indexes, which are our ANN indexes, our approximate nearest neighbor indexes. And with this new lens, we may actually rise to much different conclusions, but it also gives us an opportunity to really learn from these fields that have been dealing with very similar problems for a very long period of time. And so what does this all mean at the end of the day? I think one, we're actually starting to see vectors, vector search, vector indexes go mainstream. And as they go mainstream, they're actually joining a much larger body of research in an area that's been researched for a very long period of time. And we also have a ton of work to do here. And I think all of us have seen the rapid development over the past several years, but I think and can only expect more development in a lot of these ways. And ultimately, an eventual merging of these different infrastructures. Again, these things have been very distinct in the past when we think about vector search, think about search, when we think about databases, but they're actually starting to look more and more similar. And we can start to see these different technologies, these different paradigms, these different communities all coming together and learning from each other. And so with that, I'll conclude that all vector search is hybrid search. Hope I've convinced you all of this, or at least it's a problem we should start thinking about. And just want to give a huge thank you to the audience. And also a shout out to Julie Mills and Louis Brandy, who helped me pull together this presentation.
Thank you, John. So, do we have any questions for John? Straight up, the guys up front. Here we go.
Hi. So you were talking about like in place versus pre-filtering and post-filtering. Have you looked into quadrants like in place filtering? Like, what's your opinion on that?
Yeah, so there's a lot of people that talk about this, single stage metadata filtering, where this approach perhaps removes some of the pitfalls of your pre-filtering approach or your post-filtering approach. And it's actually pretty easy to see how that may work with something like an inverted index structure, right? In some ways, I have these posting lists of embeddings that are similar to the one that I'm searching across, and then I'm intersecting those with other posting lists that fit some criteria or some filter. Now, the challenge here is that that approach only may apply to, let's say, an inverted type of file index structure, which is something like face. I believe Quadrant uses something like HNSW to actually do their vector search. But then you can think about, there's 8, 10 plus different type of popular similarity search, vector search algorithms. And so there's actually a lot of ways to think about solving this problem. Quadrant, I'm sure, has a unique solution. I haven't tested it myself, so I can't comment on how that works and if there are edge cases, if there are situations where that becomes a challenge. But we're already starting to think about really clever ways to combine these two. And so I think that's a great example of how one very popular vector database is approaching that.
Okay, and just to remind people watching us on Zoom, please do submit questions through the Zoom chat, and we'll ask them on your behalf. We have another question from the room.
Hi. You talked a lot about filters, but especially for RAG apps, how do you have any recommendations on how you would go about extracting filters from user queries themselves without having to specify it manually?
Yes, that's a great question. And I think that probably expands much further beyond how we're thinking about searching across documents and actually applying those filters. There's a lot of research that's been done over the past 5 to 10 years. We have like entity extraction, different approaches, especially in the machine learning community, to actually look at a blob of text and let's say pull out things that are like pronouns or things that have very specific meaning or are very specifically related to the content. And so I think that is probably more in the machine learning community in terms of actually extracting what those filters could be. But a lot of these filters may extend beyond what is actually in the user text, right? So one of the examples that we use is perhaps you only want to reference documents that have been updated or created in the past 30 days. That can apply to almost all the queries that you may run. If we think about we want to surface products that a user is looking for, but there's inventory associated with that product, right? We don't want to surface products that have been sold out or not available. And so yes, there's definitely things that we can do and think about in terms of extracting entities from our query text and then applying those as filters. But then there's a whole other space of filters that can apply regardless of what that text actually is. And so I think in both of these situations, we can think about how this applies. But you necessarily don't need to solve this extraction problem to take advantage of some of these filtering techniques and some of these filters you may want to apply on your data.
Okay, thank you. We actually have a question online to go to first. Sean Springer asks, read the pre-filtering approach. I don't get how step 1 works. How do you impose a classic relational database query against an index full of vector data?
So let's go back to the slide here, just so we all know what we're talking about. So with this pre-filtering approach, right, we have 2 steps. The first is we want to pull out all the candidates that are available. And then on the second, we actually want to scan across all those results and determine which of those are the most relevant. So with this, I can actually think about this as completely 2 separate systems if I want to. So on one end, let's say I have a SQL database over here. I query that database for the documents or for the pieces of information that meet my criteria. And usually when I'm using this pre-filtering approach, hopefully I'm only returning a small subset of these documents. But in many ways, this could be the entire collection for all that matters. And so now I've extracted all these documents from my database, and they're potentially residing in memory. They could be residing within another service. And then within that service, within that potentially separate application, I'm then doing an exhaustive search across those. So all these documents have an embedding associated with them, and then I'm running this computation across those embeddings. And so where that resides could really be a multitude of different places. But in the case where we have a small number of documents, this is a process you could just simply run in memory. And you wouldn't need more or less a separate index to actually perform that computation.
Thank you. So coming back to the room, you have a question here.
Thanks. It's more of a clarification on the first question that was asked. I understood you to be saying that you consider implementations of HNSW to be examples of this kind of converged infrastructure that you're talking about, where you're combining, when you're doing like in-place filtering with a vector search. Is that a correct understanding of what you were?
Yeah, so I think there's a ton of products, tools that are already trying to solve for this. I don't think it's anything novel thinking about combining vector search plus, let's say, the metadata filtering. I think there's been amazing advancements made there. But what happens when we think about other type of indexes that you may want to use with your vector search? I think in one case, which I think is really interesting, is something like a geospatial index, right? We talked about the example where we may only look at accounts that are within a certain geographic area or region. I don't know if that's been solved for yet. Not saying it has or it hasn't, but I think that introduces another realm or a different problem. What if I also want to compute statistics on my documents? Perhaps let's think about, recent page views. How many people have visited a document in a given amount of time? That's something that actually runs really well. It's like a columnar store and perhaps like an analytics type of database. And again, a different type of index. And so I think there's actually been a ton of advancement in research in like metadata filtering plus vector search. But a big thing I want us all to think about is that there's a ton of different indexes, a ton of different search patterns, of different algorithms that we may also want to use with our vector search. And that's where I think there's a lot more learning that we can do and a lot of research that we can really borrow from.
Great, thank you. So we have no more questions online at the moment, but that's somebody right over there. No, you need the mic so we can hear it on the recording. So here we are. I'll pass this and, actually I'll come past. Thank you. Sorry, sorry. You can tell I'm British. I apologize for everything.
How's it going? I'm Joe. I think you raise a good point about merging different indexes beyond metadata filtering, right? Like metadata filtering is something that's, we all kind of think is a really powerful thing, but is pretty straightforward. You can think a lot of different ways of applying it. But a lot of people here, I think, are coming from a place where there's an established keyword search system, that we built up that's powerful, right? And merging that with your vector search index is kind of how you get to the next level. And there are a few ways that I think, research and people have brainstormed around this, right? Like you can use your keyword index separately and a vector index that are separate, and you merge them together in some sort of way as a way of metadata filtering, like run my keyword search, use that as a filter to refine my vector search. Or someone might say, create a singular sort of index. Like I know people like Elasticsearch and Vespa have been pushing, like you can make one index where you have both, you're running like a reciprocal rank fusion across both your BM25 and your vector similarities to merge those. And I was wondering if you have any experience or insight with customers you've worked on sort of, is there kind of like a decision about which of those sort of may lead to possibly better results or how people have done it? Because I know that it's very easy to say, take your keyword search, run that, use this as a filter to drive your vector search. But it's much more difficult to build a coherent index that can do all of this in one specific ranking operation or one specific search relevance function that you're creating from this index. So do you have any insight that you've maybe gathered from your customers about these different kinds of more advanced approaches than, like just simply like saying like, I can identify this, let's just restrict this space to that. There are like new developments there.
Yeah, so from the customers I've worked with, a lot of times they're doing this in completely separate systems still, right? So we may have vector database over here. We may have different search solution over here, essentially running those queries, those searches in parallel. At the end, I have a conglomeration of results, and perhaps then I have kind of a re-ranking model that is then kind of extracting and giving me, let's say, the top 10 most relevant. So that's the biggest paradigm I see today. And I think there's been and continue to make a lot of progress here as we think about text search and vector search working together. And I think we can, I think that's again a problem that a lot of people are researching, and there's a lot of potential ways we can solve that. And again, having this kind of singular, holistic index that supports all these different patterns. But then what happens, again, what if I want to add in a different type of indexing structure, right? In this case, and as we talked about, metadata filtering. Is that a separate index? How would that work with this now kind of holistic or perfect index that's blending text and vector search? Again, we could go to like the geospatial example. We could also go to like range indexes when it comes to relevance and timing. And so I think the future that I see is we're still going to have multiple indexes, right? And if it's very domain specific, and if we know we only want 2 patterns, I can very much see you using a specific solution. But let's say you expand different use cases, you may augment your application, you may want different types of results or provide different results in different areas, you automatically may get into this indexing problem. And so that's, I think, what I'm really like pushing forward for us to think about and start solving, that in some ways we may never actually have this like sufficiently clever index. And we should spend more time thinking about how to actually balance and search across these different indexes. And so ultimately I see a much more of a kind of conglomerate solution across the different indexes that we have today.
Okay, we're going to just take a question online, and then we're kind of running out of time, I'm afraid. Sorry, Stavros. You'll get a chance, I'm sure. Let's see. Huan Feng, does the criteria to classify a filter selective or non-selective depend on the domain?
I think like any application is going to be domain specific in a lot of ways, but I wouldn't say any domain, has, purely selective filters or purely non-selective filters. Now, I'm sure there are situations where that's the case, but I think what I've seen, and again, I think some of the examples we click through is that usually see a blend. Sometimes there's very selective things you want to filter on, but other times there may be things that are less selective. And I think one of the challenges here, let's say when you're initially developing a prototype, putting together a POC, MVP, you may feel like you fit into one of these categories, right? Typically, my filters are very non-selective or typically very selective. But again, the moment you get that in the hands of customers, you start to see how they're using it and what they're experiencing. You want to augment that. You want to change things. You want to improve things. Again, you may encounter a need then to adopt, let's say, a different type of filtering, a different approach, which may be selective or non-selective and different from that initial set that you had scoped.
Thank you. Okay, I think we're going to end it there. Please give a huge round of applause to John.
Thank you, everyone.